So let's go over a couple more theorems. I decided to go ahead and finish these. So this is another theorem about polynomials. Try that again. Okay, so this is a theorem. This is on polynomials. It was worth just talking about polynomials actually in general. So, so you have a polynomial p of x equal to a sub n x to the n, a sub plus a sub n minus 1. Oops, I wrote plus. Minus 1, x to the n minus 1, etc. Dot, 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 down to a sub 0, a naught. So using the limit laws above, which we will maybe prove a couple in 2.3, is what you need. You need the precise definition of limit to do those, which we'll do later. Then you have, so if you have a polynomial, leaving off a few little details here, but that's okay. So the limit of p of x as x approaches c is just the function value, is just p of c. So we just evaluate at the function. And then you have some other theorems too for radicals. So let's let or suppose that n is in the set of natural numbers. C is a real number. C is in a set of reals. Then 1. If n is odd, then the limit of the nth root of x as x approaches c is the nth root of c. So you can evaluate at c. If it's even and positive or non-negative, so 2, if n is even and c is greater than or equal to 0, then you can evaluate. So it has to be positive inside the radical, right? And with an even root. Then the limit of the nth root of x as x approaches c is equal to the same thing, nth root of c. So that's, of course, provided that you have positive numbers going in. Let's go ahead and do the composition. Okay, so next theorem. This is on composition. One of the reasons I decided to do this is just to review some of all this stuff. So it's composition of functions. We have f and g are functions. And if you have the limit of f of x as x approaches c, so c is real. I'm leaving off some of the details again. Okay. Equals L. L is real as well. And the limit of g of x as x approaches L, right? You're approaching the value L is equal to g of L. Then we get that the limit of g of f of x as x approaches c is equal to g of L, right? So you're substituting into the function basically. All those would be able to be, again, you'd have to prove those using the precise definition, which we'll do later. Okay, so here's a quick example. So this is when I would say maybe for example to apply a couple theorems above. Evaluate the limit of x squared plus 2x plus 1 cubed as x approaches 1. I'm kind of making it easy here, right? So this is basically a composition of functions in a polynomial. So basically you have f of x is the polynomial x squared plus 2x plus 1. You don't have to write all this stuff out. I'm just kind of showing you what it looks like. And g of x is be like your x cubed, and then you can just evaluate essentially. So if there's no indeterminate forms, you can just plug it in. Just substitute it in, plug it in, you're good to go. And it's cubed, and then you evaluate that. 1, 2, so 1, 2, 3, 4, so it's 4 cubed. 4 cubed is 64. And that's your value. Next is the next important theorem. This one we'll use for a few things. This is called the sandwich theorem. Oops, I just wrote theorem there. So sandwich or squeeze theorem, depending on the book. I think our book uses sandwich theorem. I've seen it in other books called the squeeze theorem, so you'll see what I mean. So here's the idea. I'm going to do it graphically first. Pretty straightforward concept, mathematically, graphically to look at, and you'll be good to go. So suppose you have in some interval, so we're going to go around some interval like this, and let's say here's your A, and your x value is going to be approaching that. So your x value, arbitrary, inside some open interval is approaching A, all right? So it's approaching that value. So we don't know what that value is, actually. Let me erase that. So you have some function below, and it might be doing something like this. Okay, then you have another function above that's, say, doing this. And we'll do whatever. So that's your function g. And we'll say this is our function h. Then if you have a function that you can always show is in between g and h within some open interval, then the limiting value is going to be the same. So this limiting value here will be the same. So you're squeezing it between those two functions, g and h. There's your f. So this theorem says, and that makes sense, so the limits, if the limit of g and limit of h go to L, so L, I forgot to write that part, this is L, and you can show that f is between g and h for all values within an open interval, then the limit of f must approach L. So it's stated like this. Let me move that up a little bit. Theorem says if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x in an open interval containing A, except possibly at A itself. So except possibly at A itself. And if the limit of h of x equals L as x approaches A, which is equal to the limit of g of x as x approaches A, then the limit of f of x must do what? Must equal L. So it makes sense when you're smashing it between two functions like that. I'll look at an example later. We'll use this on a couple of very important theorems later, but Intuitively, it makes sense. It's tough to show it or prove it mathematically, but of all this stuff, the tough part is actually showing that this is true. Verifying that f is between g and h for all values is usually the tough part. Showing those inequalities hold. Okay, so that's the squeeze theorem. And we'll look at examples in the problem sessions of one of these at least. And next we'll go on to 2.3, the precise definition of limit. I might have it posted soon. I'm trying to make these generic, so I'll post 2.3 next when I get to it. Thank you.